Okay, so to start off our last session, we have Eric Walkingshaw from OSU, who's going to talk to us about variational programming. So please take it away.
I'm up here from Oregon State. I'm our one representative here. So I wanted to briefly show our group. So this is just the programming languages group. We're pretty small, just 2 faculty members and some grad students. A couple grad students were out sick on this day, unfortunately. And then we've got about 4 software engineering faculty members as well. So yeah, I'm going to be talking about variational programming. And this work was originally motivated by a problem that comes up in the context of highly configurable software systems. So the idea here is that you have a code base, and this represents not just one program, but lots of different programs. For example, it's a software product line, or it's an open source program that has lots of configuration options and features that can be turned on or off. And so the usual workflow for sort of making a running program out of this code base is the first thing that you do is you configure it. So you pick the features that you want, and you generate a program that can actually be compiled. And then maybe you do some program analysis on that, make sure that it works, run a test suite on it. And then if it works, you can go ahead and deploy it. So the problem with this workflow, especially in the context of open source software, is that often the person that's generating and evaluating this program that wants to deploy it is not the same person that wrote the code in the first place. Right? So the person that wrote the code, they sort of understand all of the configurations. The person that generates a configuration, it's very likely that you can generate a configuration that's never been generated before because these things have hundreds or even thousands of configuration options. They don't know what to do with the error that they get back. They don't even maybe maintain this code at all. So this process finds the errors too late. But the person that writes the code, they can't anticipate all of the configurations that somebody might want to generate. There's just way too many of them. So the solution to this problem is something that we call a variational analysis. So what we do is we instead evaluate the configurable code base directly, and we call this a variational analysis. And what this gives us is it gives us a variational result. And the key thing here is that this variational result conceptually represents the result for all of the configurations that can be generated from this program. So if we apply a configuration to the original program and run the standard program analysis, we get the same thing as if we apply that same configuration to the variational result. And so now we can do things like evaluate all of our configurations in advance so that the person that generates the configuration that they want to deploy doesn't encounter an error. So we've done lots of work on developing languages, theory, data structures, and algorithms to do this sort of thing correctly and efficiently. And collectively, we call this variational programming. So I want to give so the first example of this that we did, so this is when I was a grad student, is variational typing. So this is just a sort of concrete instance of this last slide here. So in this context, so normally you have lambda calculus, you run the Hindley-Milner algorithm, you get a type. You infer a type for that program. So here we have a variational lambda calculus, and we can run variational typing on that and get back a variational type. And the types that are represented here correspond to all of the types of each of the configurations. Okay, and in order to implement this variational typing box here, we need variational programming. So I'm going to give an idea of what variational programming is by an example. This is sort of a fancy name for a simple idea. The fundamental concept in variational programming is something called a choice. So here's an expression with a choice in it. A choice has a dimension, so in this case A, and 2 alternatives. So we can select the left or the right branch from a dimension, and we get the corresponding alternative. So if we were to evaluate this program with the choice in it, we'd get back a variational result. With a choice in the corresponding dimension. If we have multiple choices in the same dimension, they're going to be synchronized. So if we evaluate this, we'll get 12 and 23, because if we choose the left branch from A, we get the left branch of both choices in A. If we have choices in different dimensions, they're independent. So if we evaluate this program, we're going to get 4 different alternatives corresponding to all the 4 different ways that we can configure this expression. The alternatives of a choice can have different types as well. So here's an example of a choice where one alternative is a Boolean and one alternative is an integer. And so we have choices also at the type level here. So here, a choice in the expression induces a type with a choice in the same dimension. And so here's another example of an expression with two differently typed alternatives. And what we can see here is that when we have sort of a structured value, in this case a type, we can push the choices into the type. So this type is exactly equivalent to this choice type here, which more directly corresponds to the type of this expression. So successor has type int to int, even has type int to bool, and so we can factor this common int argument out. Okay. So of course, we can evaluate. So here's another example of applying an example. Applying two different functions that have two different types to two different values. So the not function expects a boolean, returns a bool. Even expects an int and returns a bool. And what we see here is that in both cases, the result is false, right? So we have two completely different expressions, not applied to true and even applied to 3, but both of them return false. And so what we return here is just the value false. So we no longer have a choice. This is equivalent to this expression, but we can sort of forget about the fact that we had a variation there because we don't need it going forward. And so this is going to be key to sort of computing efficiently with these things. Here's just a more complicated example here. This represents 4 different expressions: successor applied to 2, successor applied to 4, and even applied to both 2 and 4. And what we can see here is we get a more complicated variational value where we've had some sort of folding inside of some sort of collapsing inside of a choice. Okay, so that's sort of just preserving variation across computations. We can also reflect on the variation that's in a computation. So here's an example of a function vsum. I'm not showing how this is implemented, but basically what this is going to do is this is going to look at the alternatives that are in the result and sum them all up. So it's going to sum up all of the results here. So this is going to sum 12, 13, 22, and 23, which gives us 70. We don't have any variation in there anymore because we've accumulated all of these alternatives. And we can also do things like pick out a particular variation here. So here again, we've got the same expression. And what we want to know is we want to know what's the maximum value in there. And so we get back the value 23. But oftentimes, we also want to know which configuration that value came from. And so we can return that in the result as well. Okay, so that's variational programming by example. So the first challenge that comes in here is that the space of potential variance grows exponentially in the number of dimensions that you have. In the worst case, this is obviously very bad. So the trick to sort of doing this is, first of all, to share as much as possible. So we don't want to introduce choices until we absolutely have to. So that's what I mean by splitting late. And anytime we have two alternatives that converge to the same value, we want to eliminate choices as soon as we can. When we have structured data, we also need to use clever data structures. I'll talk about that a little bit more here in just a second. But probably the most important thing to do is just pick the right domains. So some domains don't have enough sharing in them for this to really work. So if you're doing numerical simulations or something like that, this probably isn't going to work. The other challenge is that variation is sort of like sand. So sand gets in everything. And variation also gets in everything. So when you're writing one of these variational analyses, the variation just gets into every incremental data structure and every incremental value that you're working with. So in particular, when you have structured data, the idea of choices just sort of starts to break down. So here's a really simple example where we have a choice between two lists. So we have 1, 2, 3, and 1, 2, 4, 5. And so we can see that there's some redundancy here. So ideally, we could factor this out in some way. So one idea is that we sort of push the choices into the list. But then it's sort of not really clear what to do here because we have an element in one variant and not in another. And so we need some specialized representation for variational lists. And it turns out we sort of need lots of specialized variational data structures for different kinds of structured data. And originally, I sort of had this vision that this would all be very systematic. And the variational data structures that work best so far seem to just be ones that we've developed ad hoc for each particular domain. So this is something that really still needs more work. The other problem is what to do about side effects. So when we have choices in programs and side effects, if you, say, print out something inside of a choice, we can't sort of make two copies of the world, one where we printed out the value and one where we didn't. So what do we do there? And this is something one of my grad students is working on. OK, so returning to variational typing real quick, this is sort of an ideal domain for this problem. So there's lots of sharing, lots of configurations of a program end up having the same type. So that's great. It turns out that for realistic programs, this scales roughly linearly with the size of the program. So we don't encounter this explosion of the variation space. This even scales to programs as big as the Linux kernel. So Christian Kestner at CMU implemented a tool called TypeChef that is basically the same ideas here. And he can type check all the configurations of the Linux kernel. It takes about a day, but it's doable. OK. So variational typing is sort of the ideal scenario. We've done this also for several other, us and other people have done this for several other analyses of software product lines. But it seems like this idea of choices should be more general than that. So for a while, we sort of felt like we had this cool hammer, and we were looking for nails to hit with it, which is always sort of an awkward position to be in. That's not really the right way to do research, right? But yeah, this is what we did, I guess. So we started thinking about what are the properties that make a good nail. So it needs to be something that has lots of variation in it, right? Because this is where this variational programming idea really pays off. But it also needs to have lots of sharing between the different variants. So types, good. Numerical simulations, bad. OK, so sort of the key insight was that the original problem, or the original program that we're working with doesn't necessarily need to have the variation. Instead, we can use the idea of variation to explore hypothetical situations. At points where sort of in a traditional, say, program analysis, we have to make a decision to commit to one path or the other, we can instead just introduce a choice and explore both paths. OK, so let's look at an example of that. OK, so Michael talked about fault localization. So the problem of error location in the context of type checking is related to this. So the idea here is that when you run your type checker, sometimes you get a type error. And locating where the actual conceptual error that caused that type error is a hard problem that's been around since the 80s. And I think the research probably looks very similar to fault localization, where there's sort of all these new approaches to this, and everyone's better than the previous one, according to the papers, including ours. But all right, so here's an example of a program. So there's no variation in this program. This is just a plain Haskell program that exhibits this problem. OK, so here we've got, first at the top here, we've got a definition of the fold function. So this is a left fold. We've got flip, which flips the order of its arguments. We've got reverse, implemented in terms of fold and flip. And then finally, we have a function palindrome that checks to see if a list is a palindrome by checking to see whether the original list is equal to the reverse of the list. Does anybody see the bug in this program? Oh, rats. OK, so the bug in this program, well, let's see what GHC has to say about it. So here's what GHC says. So GHC gives us this, it's sort of complicated, but ultimately it gives us a location for the error. So it says the problem is in reverse x's equals x's. OK, that looks fine to me. So it turns out that's not really where the conceptual source of the error. So the conceptual source of the error is that our base case of fold L is wrong. So the very first line of fold L is incorrect. That should just be, we should just return the base case there, not a list containing the base case. So there's an error in the base case of fold, but fold without any type annotations actually type checks. The use of fold later in the reverse function also type checks. We don't actually detect the error until sort of this 2 uses later in the palindrome function when GHC finally detects the error. OK, so this is a problem, and we can see it exhibited here in GHC. OK, so there's been lots of work on how to improve error location. So the solution, so this is actually work by Sen Chen and Martin Erwig, so 2 of my collaborators. But this is a really cool application, I think, of variational programming. So basically, the problem is that locating the cause of a type error is hard. And the reason is that type inference commits too early. So here, when fold type checks correctly, it commits to the type that it infers for fold. And But the problem is that a successfully inferred type could still be wrong, right? So just because type inference succeeded doesn't necessarily mean the type that was inferred is the correct one. So the solution is that when we infer a correct type, we still sort of keep open the possibility that that type could be wrong. So, we assume that the type either could be correct or could still be wrong. So the way counterfactual typing works is that we basically perform variational type inference. So error tolerant here means that if one particular branch of type inference fails, we don't fail the whole process. This is important because we're dealing with a program with type errors in it. But for every sub-expression, so every single sub-expression in our program, when we infer a type t for the sub-expression e, we instead introduce a choice type here. So we instead say e is a choice in some dimension d. That's either the type that we inferred, or it's a fresh type variable here. So the dimension is fresh, and the type variable is fresh. And we do this everywhere. And when we're done, we get this variational result with lots of dimensions in it. And we're going to search that variational type that we get back for a value that's not an error type, and that has as few right selections as possible, right? So right selections correspond to places where the inferred type was wrong, right? So we want a type where we have to, this basically is a measure of how many changes we have to make in order to fix our program. So it's basically saying what was written here was wrong. And so we're sort of using this type variable to capture that we might have put anything else in there, anything with a different type. And so we search our variational type for something where we have to make as few right choices as possible. And it turns out that this gives us the location where we have to make the smallest number of changes to find the error or to fix the error as possible. And then we apply some other heuristics that help us be better than everybody else before us. Okay, so that's one problem. So oh shoot, I'm slightly over. So we also apply this to gradual typing. It's really cool, but I took way too long explaining the other thing. So let me just say real quick. So gradual typing is all about mixing static and dynamic types. But a big problem with them is migrating between gradually typed programs. So the problems that can occur are that when you're adding type annotations, you can get into a place where you sort of can't add any more type annotations, but you're not in the most statically typed program. There's also potential for huge performance degradation. So there's papers written about how gradual typing is broken fundamentally because of this performance degradation problem. So basically the idea is that we do the same trick that we did in counterfactual typing, and we can basically introduce choice types for every parameter and explore the whole space of potential gradual type migrations and find ones that satisfy different criteria that we want. And so yeah, this paper was at Popple this year. I put a little crossed fingers next to ICFP. Our reviews were good, so hopefully in a week we find out that we have an ICFP paper on it too. Okay, so sorry I went over. Variational programming makes variation explicit, and we can use this to explore hypothetical scenarios. Thanks.
Okay, are there any questions for Eric about variational programming? It's late in the afternoon, don't be shy. One thing I was curious about, there's like, there are a lot of, you mentioned like simulations is a bad option, but actually there's a lot of simulation packages that have a lot of variations for accuracy. So like Seagal is the one that sticks out of my mind where they have like 80 different flavors depending on like how much you're willing to spend on floating point. I wonder...
So I guess the reason I assume numerical simulations will be bad is because we never have this situation where alternatives converge to the same value. So in typing, this happens a lot because different configurations have the same type, and so we can forget about the choices, basically. But yeah, I don't know. I mean, we can talk about this more. Maybe in this case where it's different amounts of precision, maybe this does occur.
Well, actually, the problem is they don't converge back, so maybe you're totally right. That's why there's, but yeah.
All right.
Any other questions for Eric? Okay, so up next, oh, I'm so sorry, Doug.
I have no idea if this is a good question, but so you mentioned that you've had trouble sort of finding anything like general with variational data structures. Is there something about like derivatives of types that would help here? Like it seems like your variational data structures are like you're modifying something in some way, and you want to record those modifications. So
yeah. So I mean, I thought about this, like using zippers or something like this to. Yeah. So I still think there's potential for this here, but the problem is that. Yeah. So I mean, the problem is just that you can get better performance than sort of introducing choices in a derivative of a data type by just doing something special. So I mean, yeah, this is hard to say without examples, but yeah, we can talk about this offline maybe.
Awesome. Okay, and let's thank Eric again. Oh, okay. So up next, Brad's going to tell us what's been going on with the Chapel language at Cray.
Great. Thanks. So I'm Brad Chamberlain. I'm a principal engineer at Cray here in Seattle, and I'm the technical lead for the Chapel project, which I'll be talking to you a bit about today. This is the official talk for my or title for my talk, but I have this bad habit of making up dumb titles the night before I give talks. So this will make more sense as we go along. If you're not familiar with Chapel, it's a productive parallel programming language that we're developing at Cray. It's portable and scalable, which means it can run on your laptop, your cluster, the cloud, on a Cray. And it's open source and collaborative, which means we're developing it at GitHub under the Apache license. The two main goals of Chapel are to support general parallel programming, which you can think of as if you've got a parallel algorithm in your mind and some parallel hardware you'd like to run it on, Chapel should be able to do that. And the second goal is to make parallel programming at scale far more productive than it is today. Now, that term productive means different things to different people. One way that I'll explain it is to compare to other languages. So we want a language that's as easy to read and write code in as, say, a Python, but yet is as fast as a Fortran, as scalable as MPI, which is how most people do large-scale HPC programming today, as portable as C, as flexible as C++, and as fun as your favorite programming language so that you get excited about using Chapel. So one way that I'll kind of visualize how we're doing here is by looking at the computer language benchmarks game. And here I've taken the languages that are involved in the game, and I've plotted 2 points for each one, which are the geometric means of their fastest programs and their smallest programs in terms of code size. So the closer they are to the bottom of the slide, the faster the language is. The closer they are to the left, the smaller the codes are in the language. And so as you'd expect, the scripting languages are further off to the left here, but much slower. And then if we zoom in on who's down there at the right, we see C, C++, Fortran, and Rust. But of course, their codes are also much bigger. Now, I've left Chapel off here, but if we add the Chapel entries to this, then we're sort of off here down to the left, which you can think of as being productive because you're sort of fast and small. And if I zoom back out, we're sort of, again, uniquely down and to the left compared to where most other languages fit nowadays. Now, of course, we all know that language succinctness isn't necessarily the best metric of productivity. So the website also lets you go in and look at the programs, and for the Chapel, you can see things like these high-level co-begin and co-for-all constructs, which create tasks. Whereas in the C entry, you can see things like schedule get affinity and things that hopefully most of you have never had to deal with in your life. Okay? So that's a little bit about Chapel. When I was approaching this talk, I sort of said, well, I could talk about a number of things, and my reviewers each wanted me to talk about something different, which I should have anticipated. But one of the quotes that stuck out for me was this one, which said, Chapel's been around for quite a while, and it still seems like a niche language, which is one of the things that sort of hurts your heart to hear, but is arguably true, and I think a lot of people share this perspective. So I wanted to dive into this a little bit and say, first of all, are we a niche language? And one way in which you could view us as being niche is that Chapel was originally designed for HPC, and HPC is arguably a niche field within computer science. But that said, if we step back and look at Chapel, Chapel cares about performance, and I think a lot of people, even outside of HPC, care about performance. We've heard a lot about that today. Chapel cares about programmability, and I think the rise of things like Python show that people care about that. Chapel cares about parallelism, and multi-core means that we're all arguably able to be parallel programmers nowadays. And it also cares about scalability or distributed memory. And with the rise of cloud computing, you can see that that has become bigger and bigger over time. So I would argue that Chapel, while developed originally for HPC, actually has a lot of applicability outside of HPC as well. And as language matures, we're hearing that from a lot of non-HPC programmers as well. Another way you could consider us niche is that we really have a very modest-sized user community. Like it's not it's not a Python, right? We'd love to be as large and successful a community as Python is. But something you have to know is that historically, if you came to me and said, should I program my next production app in Chapel? Historically, my answer has been, no, probably not yet. And that gets me to the quiche part of the talk. So I think a lot of people in the community who've maybe heard about Chapel over its lifetime say, like, well, why aren't more people using this delectable language? And in their mind, they've sort of got this picture of this lovely quiche that we've been making. But the reality is that over the large fraction of the program's history, we've been putting this quiche together. And you probably don't want to eat it just yet, but read the recipe, sample the ingredients, see if you think we're on a path that's going to be attractive to you. And I'd say where we are today is kind of here where it's perhaps almost fully baked, and maybe it's time to take a look at it again if it's something that's of interest to you. So going to the other part of that reviewer comment that has been around for quite a while, so that's accurate as well. Chapel came out of the DARPA HPCS program that ran from 2003 to 2012. At that time, we were very much a research focus, a small team of 6 to 7 people. And I think we accomplished some great research objectives in the parallel language area. But at the end of the day, we had a research prototype. We didn't have something that people could really use. So what we've been doing since then is what we call the 5-year push. This has been a 5-year effort to basically move Chapel from research more to product. And we doubled the size of the team as part of that. And we focused in these 3 main areas: performance and scalability, building up the ecosystem around Chapel, and fixing things in the base language that weren't directly related to parallelism or scalability. And this third one is probably of most interest to this crowd, but doesn't fit at all in a 10-minute talk. So I'm going to touch slightly on the first 2, and I'm going to compare kind of then, where were we at the end of HPCS and the start of this push, versus now, where are we today? And I'll start with the ecosystem, then versus now. So when we came out of HPCS, in terms of documentation, we had a PDF language specification, we had a quick reference sheet, we had a number of text-based README files, and we had some primer examples that taught you the language through comments and code. And now we're at a point where we have over 200 modern hyperlinked web-based documentation pages, and when you surf to Chapel, it feels more like a real language and less like somebody's experiment. In terms of libraries, at the end of HPCS, we had about 25 library modules. Some of them were documented in source code. Some of them were not really documented at all. We're now up to a point where we have about 60 library modules. All of them are documented on the web, and many of these have been user contributed. And then in terms of tools, at the end of HPCS, we had highlighting modes for Emacs and Vim. We had Chapel Doc, or at least a rough draft of it, which was a documentation tool. And now we have those, as well as Mason Package Manager, a C to Chapel aid for interoperability, Chapel tags, which allows you to search your source code, bash tab completion, and then this performance visualizer over on the side here, Chapel Viz. So a lot of great improvements to the ecosystem. Performance is another thing that's traditionally been a problem for Chapel. If you ask most people in HPC about Chapel, they'd say, oh, it's that really pretty language that performs really terribly. And in HPC, of course, that's kind of a killer. So over the last 5 years, we've done a lot with performance. This is a bit of a laundry list, but in short, we've done a lot of locality-oriented things, particularly within multi-socket nodes, and a lot of communication reduction across nodes. And so if I went back to where were we then, this is a stream performance benchmark, and higher is better, and I'm adding nodes across the axis at the bottom here. And so you can see that as we added nodes, the performance got better as you'd expect. But if you compare that to where we are today, we were about a third of the performance we're getting today. And of course, now you should be suspicious and say, well, how do we know that you're good today? Well, if we compare to the reference version in green here, you can see that we're tracking it pretty closely with just a little bit of hit due to our elegance. Looking at a second example, this is a stencil computation at that end of HPCS time period. Again, it's getting faster as we add nodes. But if we add today's onto there, basically the red line goes all the way down to the axis. We just were terrible in terms of raw performance then. And again, if I add in the reference, you can see that we're tracking it very closely today. So you can look at this across a number of HPC computations. These handle things like just local loops, embarrassingly parallelism, bucket exchange, stencils, global random updates. And in all these cases, we're doing quite well compared to the reference version. I'll go into one more in a bit more detail, the global random updates here. This is the code for the MPI version of this benchmark. As you can see, it's almost as elegant as Chapel. At the top there is a comment, and this comment tells you what this code does. Basically, it's just doing random updates to a globally distributed table. And this is the Chapel loop for that same kernel. And as you can see, the actual computation is about the size of the MPI computation. This is another case where we're not only scaling competitively with the reference version, but in fact outperforming it. OK, so what's next for us? Next week, we've got our annual workshop. It'll be up in Vancouver, so it's local-ish this year. If you've got friends or colleagues or students who are interested in parallel computing and languages, send them up. It's generally been considered a high-energy workshop. And as we look forward, we're kicking off a new 3-year effort where we're going to be continuing to work on performance and scalability, targeting libfabric, targeting GPUs, targeting the cloud, and working on AI. This is our team at Cray. Again, there are about 13 of us working on it full-time at any given time. We also have an intern program, and we'd love to have your students apply to that. It's an open source effort, so we have community partners as well. You notice there's a sort of disturbing lack of Pacific Northwest education and industry on here, and we'd love to correct that if anyone would like to collaborate in this area. And I think just to leave you here, I will just skip ahead to my summary slide. So we've made huge progress over the past 5 years. We think Chapel is ready for production, but I put an asterisk there because different people have different ideas of what production means. And again, we're open to collaborations. Last thing I'll mention is that we have some Chapel swag in the form of screen or glasses wipes up here on the chair if you need one. And I've got 5 minutes for questions. If you have any.
I can start off. I have one question. So you showed how versus at the end of sort of the DARPA program,
HPCS, right?
Yeah, at the end of HPCS, compared to that, your performance is way, way better.
Right.
Is the code the same? Are you running the same program and getting that much better performance, or are the implementations updated as well?
Yeah, no. So in this case, what we did was we took today's code, and we actually took that old release and ran it on today's hardware. So it was as apples to apples as possible. And in some cases, we had to take the code and maybe sometimes we relied on a newer feature. We had to rewrite that using a slightly older feature in order to get it to run on the old version. But by and large, it's sort of, it's more or less the same user code that you would write. So it's meant to be as fair of a comparison as possible. And it just speaks to how poor we were in that time frame in terms of performance.
Another thing I'm curious about, so in this distributed setting, I mean, if you have sort of some kind of like work stealing or something, depending on how the schedule ends up, you might do floating point operations in a different order.
Yeah.
Do you ever worry about that for like even just for reproducibility? I mean,
yeah. So certainly reproducibility is a concern among some of Cray's customers, and they sort of want things just so. We don't actually do much in the way of work stealing, at least across nodes, but still as a parallel language, you tend to have operations happening in different orders and things like that. So we have ways of kind of locking down order, but of course at the expense of parallelism and therefore maybe performance for people who do need that reproducibility. But in general, you can run into the sorts of errors like we saw in the floating point talk earlier, where if you do things in the wrong order, like you may get wildly different results. And that sort of goes along with parallel computing, and unfortunately, it's the world we're used to living in for the most part.
So, and do you guys have sort of like regression tests to ensure that so I guess you have some flag that's like, make this reproducible.
Right.
I mean, it seems like that's the whole way down, right? There's like both on the network, there's across cores, and then even within the core, right? If you want to exploit SIMD, a lot of times you'll do some unrolling and reassociation. So like, I mean, there's so many levels for reproducibility for these kinds of large jobs. How do you make sure that you've actually found all of them? That seems really tough.
Yeah, I don't think we have a really good solution there, to be perfectly honest.
It's an interesting research challenge. If somebody in the region is looking to collaborate, maybe you could think about.
We would love collaborations around that realm. And I think you guys have the chops for it as well. I see 2 hands here. Charlie.
So you said you're cloud ready. How easy is it to start up, say, 100 Chapel nodes on someone's cloud?
So today, the main cloud that we've had the most experience with is AWS. And there's sort of a README that tells you how to grab the thing and set up your machine image just so and build it. We've talked about building a sort of pre-deployed machine image so you can just grab it without having to do the build and everything, but we've never quite crossed that path. We're interested in doing the same for the other major cloud providers, so if any of you happen to work for them and would be interested in seeing that, we'd love to work with you on that. But our implementation is very portable, so generally speaking, most of the cloud providers have some sort of Linuxy kind of option, and that tends to work fine for us. Okay. Question in the back there, maybe?
Yeah, I have a question. If you want to run these algorithms on the cloud, then it's typically probably longer running algorithms. The cloud, typically, some machines don't work as intended. What do you do about failure tolerance?
Yeah, so I would say that we share the HPCC has traditionally had this theme of like, just run fast, and if it fails, kind of run again, or checkpoint restart. And we haven't done anything in Chapel so far any better than that. So if the machine fails, we don't sort of do anything magical or automatic there. And that's another area where we'd like to do additional research, potentially in a collaborative manner. So again, if that's a topic of interest to people in the room, we'd be very interested in talking to you about that.
Cool.
Okay.
Okay, let's thank Brad again. Okay, so up next we have John Leo, who's going to tell us about type theory in music, which is not something you hear combined every day. I guess ornaments in music. If I know John, there's going to be types in there. Okay.
For sure.
Take it away, John.
Let's see. All right, so I would like to start out with some a little bit of background and motivation, and then I'll talk a little bit about a kind of fun project I've been working on. This is available online, but it's still very preliminary, so it will probably change quite drastically. So I'd like to start out with my favorite quote by Bob Harper, which is worth savoring for a moment. Eventually, all the arbitrary programming languages are going to just be swept away with the oceans, and we'll have the permanence of constructive intuitionistic type theory as the master theory of computation, without doubt in my mind, no question. So from my point of view, this is a personal statement. Working in anything else is a waste of time. So I love this quote. I agree with it. I'm really into both math and computer science, and I love to see this convergence. So this is a good question to ask. What would programming look like in 50 years? And I kind of agree with Bob's vision about this. We already have kind of things pointing the way. There's functional programming. There's a lot of work been done in algebra programming, mostly based at Oxford. Actually using math, with in your programming. And then now that was mostly done in the context of kind of pure functional programming, but now we have dependent types where you can do even more math. And then there's even newer things coming out now. There's cubical type theory and so forth. But there's also a question, who does the programming, right? Because, certainly from my experiences, most programmers hate math. So are they really willing to learn all this? But, I don't know, maybe 50 years from now, the computers will be programming themselves. But I think they'll be doing it written in and programming in type theory. All right, so given this is the goal, how do we actually get there? So we have finally some kind of industrial strength functional programming languages, Haskell and OCaml. So we could try adding dependent types to them, and certainly that's being done for Haskell. And even now in Haskell, you can kind of fake dependent types using a ton of extensions, but it's very ugly. Another way to do it is to take some, language that was designed from the start for dependent types, something like Agda or Idris, and try to make it practical to use. And I think it'll be interesting to see which one of those two wins out. Meanwhile, how do we even program using dependent types? This is really something that no one's done yet. No one's trying to write dependently typed programming, for industry or whatever. And I've done functional programming in industry, and even then, it's not exactly clear, what's the right way to write functional programming and stuff. It's still kind of even in its infancy, and dependent types is even, beyond, not even up to that level. And it's clear there's still going to be a lot of, both theoretical and practical advances needed to get to this point. So anyway, these are all interesting things to look at. What I want to kind of concentrate here on is let's actually start trying to program using dependent types. So going back a little bit, when I was first learning Haskell in 2014, I came across this wonderful book by Paul Hudak and a system that he had written called Utopia, which was a system to do music in. And I'm very interested in music, and I've done a little, composition and stuff like that. But I'm very lazy because, I don't want to have to spend a lot of time on it. I actually have some music software, but none of it's been quite what I wanted to use. The Utopia was actually close to what I wanted to do. Here's something where you could represent music, using a programming language. You could kind of do mathy types of things with it. So it seemed very cool to use. The Utopia was kind of based on old Haskell and stuff like that. I thought, well, maybe I can make a better, more modern version. So I started working on something called music tools. It's just basically, the idea is a small toolkit of very small programs that have a very specific purpose, and you can combine them together, using functional programming techniques or whatever, and with the idea to help you synthesize and analyze music and so forth. So I originally wrote it in Haskell, but then I thought, going back to this thing, well, if dependent types are the greatest thing, why am I not using them? So I tried converting it to Agda. And actually, it was interesting because I actually even found some bugs in the Haskell version when I made the types more specific. So it actually already was paying off a little bit. I still had to use Haskell, actually, get anything to have I/O and so forth. But it actually worked out pretty well. And I think it's a good domain to actually start with because dependent type languages are not exactly performant yet. But here's something where we don't need incredible performance. We can kind of do stuff in batch mode, and it's still reasonably fast. And it's a nice domain, right? Music is fairly well described and so forth, but it's still fairly rich. And then the exciting thing too is I've been doing some research with Talia and Nate and Dan, and some of the stuff that we were doing looked like it would apply to this as well. So I thought, well, here's a chance I can play with this. So I wasn't sure if I'd have time to play any music, but I had some requests, so maybe I'll see if this works. So here's a little piece that I wrote, a very simple song I wrote back in the day. And this is actually, so I kind of re-implemented it in, we'll see if this works. Oh, maybe not. All right, well, sorry about that.
You might just try to play it on your speakers on the laptop.
Yeah, but then I have to figure out how to change the audio output. So anyway, well, don't worry about that. But I could show it to you a little bit, what it looks like. So basically, there's four, there's kind of four lines here: a melody, accompaniment, bass, and drums. And the melody I essentially just wrote out for now. But there's actually some structure to it, and I could take advantage of that, or maybe, what's maybe interesting is have the program kind of figure out the structure and recreate it. But as you can see, for the accompaniment, it has a little more structure, so we're actually able to use some functional programming things. You see maps and zips and stuff like that in there. And the bass and the drums even more structure, so you can make them even more minimal. In fact, the very first thing I did with Utopia was try to write like minimal version of the Hanon exercises with them, if you know those piano exercises. All right. So anyway, to get this to work and have a nice tool, we need a good representation of music. How do you represent music? And I've thought about it for a while, and I don't think there's a perfect representation. There's a lot of good ways to do it, and they all have pluses and minuses. So right now I'm using something that's pretty close to Utopia, where you have pitches and durations, so you can kind of make notes out of them, and then music out of that, and you can compose things in sequentially or in parallel. But you may notice there's some ambiguity here. You can kind of represent music in multiple ways that sound equivalent. There's equivalence kind of structurally. There's equivalent musical equivalence, and this is something that Utopia has to deal with as well. For example, you can have zero-length rests in there, which actually is a common thing you'll do if you're folding and your zero-length reg is your base case. So, and here's just even a more concrete example. For pitch itself, we can represent it as a sort of absolute pitch, which I have at the top, but then we could also represent it as a relative pitch within an octave and then paired with the octave, right? So now if we wrote all these functions using one, we want to actually use them using the other one, what do? You can convert back and forth and so forth. But the nice thing is there's some nice research being done on this that we can actually apply here. So the homotopy type theory gives you a way to first define equivalence and then lift it up to functions based on that equivalence. And now, since we're using dependent types, we can take advantage of this research and actually do it. So there's been some work on this. There's a paper, Equivalences for Free, which might also appear in ICFP. We'll see, done by some people at INRIA in Coq, and I've been kind of moving this over to AgdaWorld and using it for that. But there's still some problems here. Even though you do get a lot of equivalences for free, just the base equivalences themselves can be rather painful to define. And it seems like this could be automated in some way. And I think the work Talia is doing now should be very, very helpful for this. So even beyond equivalences, so my definition of music, I left out something that was in Hudax. He had an extra little thing, this modify control. And so this actually has some extra information, and in fact, you can even put ornaments in your music. I'm not sure I want to do it this way yet. I'm still thinking about it. But this is the way I think. Just in Stuart's talk today, he was talking about adding this native thing to the other things, and then that's going to pervade everything, right? So here too, we have this kind of core musical thing, but then we have this extra information we want to add, and how can we deal with that? And so here there's another ornaments, which Talia nicely already talked about in her talk. Which is kind of, you can think of as a generalization of equivalences, where now you have kind of more information on one side than the other. And again, you can kind of do this automatic lifting and so forth with that. So this is also something I'm adding to this. Here the main challenge has been that all this work, although it's actually done in Agda, which is nice for me, they did all it with deep embeddings, which made it very nice for them to do theoretical things with it, but we need a shallow embedding in Agda. So I'm kind of using reflection mechanism in Agda to try to convert between the deep and the shallow embeddings. So anyway, so to conclude, I think this has been a great application area, and I'm looking forward to playing with it more. I really, just like types, people don't want to, put in the effort to do math at first. It's a lot of work, but I think it pays off in the end. And then part of the goal of this project is to figure out how to minimize that work and still get the rewards of using the math.
Any questions for John? So starting. Oh, go ahead. Yeah.
So have you seen any rewards yet, or it's just too early? You're just too early to see any.
It's too early. In a way, but I think already the equivalences stuff has been really nice. So I definitely, it's very promising, I'll say. Yeah.
So there's this work, on the AI side on style transfers. People do with art, also presumably music. Like you make a box, make a box style. So does that relate to this? Or?
Yeah, I mean, this is intended to be the kind of foundation to do that stuff in. So there's actually even a lot of other work. There's a lot of stuff in Haskell going on now. There's something called harm trace, things to do harmonic analyses, and they use the type system to enforce harmonic rules and stuff like that. And this is this is intended to be like a base system that all that can be built out of. And I think I can redo, for example, the harm trace stuff using dependent types. It'll be a lot more elegant than what they're doing now with a lot of Haskell extensions again.
So you mentioned that you need a shallow embedding. Is that for the MIDI interface through Haskell?
No, it's just to get the ornament stuff to work on real Agda code. So right now you'd need to, in the deep embedding, you'd need to define all your types as this embedded thing instead of using like real natural numbers or whatever even. So they define these things as fixed points of functors in their deep embedding and things like that. So it's a matter of translating between these two worlds.
Okay, any more questions for John? All right, so let's thank John again.